Donc, pour débuter la journée, on va commencer avec une conférence du docteur Peter Kyveryga. Je vais vous présenter une brève biographie. Peter a reçu un diplôme spécialisé en agrochimie et en sciences du sol de la National Agriculture University de l'Ukraine. Et il a obtenu son Ph.D. en sciences et fertilité des sols de l'Université de Iowa State. Il travaille pour Iowa Soybean Association. Il assure la direction de l'exécution des meilleures pratiques de la collecte des données et de l'utilisation de méthodologies avancées des systèmes d'information statistiques et géographiques pour l'analyse et la synthèse des données de différents types d'études à la ferme. Il communique ses résultats aux producteurs agricoles ainsi qu'aux professionnels du secteur et de l'industrie et il dirige la publication des résultats dans des revues scientifiques et techniques. Les recherches du Dr Kyveryga portent sur la fertilisation de l'azote, la gestion adaptive, la méthodologie statistique, l'agriculture de précision et aussi le développement de systèmes de support d'aide à la décision. Il est aussi l'éditeur technique pour la revue pour l'agriculture de précision dans la revue Agronomy Journal, qui est une publication de la Société américaine d'agronomie. Donc, Peter, I give you the floor for 35 minutes.
Thank you very much for the introduction. Good morning. And thank you very much for invitation for this conference, this workshop. I'm looking forward. And so far we had very nice discussion about different issues and problems which you face here in Quebec, in Canada. And we'll discuss more tomorrow and in person. So again, thank you very much for invitation. You'll probably be surprised that my accent is not from Iowa, and neither are going to talk about soybean, right? Nicholas wanted me to focus on three key areas. One, it's the challenges of diagnosing nitrogen deficiency in mid-season in Iowa. The second problem is how we can deal with yield response variability from controlled replicated strip trials, and plus how we can reduce uncertainty in estimated economical optimum rates. And finally, I'll describe some ideas focused on farm experimentation and how we can use on-farm data coming from farmers and make decision support system to improve management and quantify risk. Iowa is unique. It's one of the Midwestern states, and very often in Iowa, we say that the key to manage nitrogen is to manage risk. So in Iowa, the common risks are nitrogen loss. This is the late season aerial image of corn canopy taken in August, and you can see that this field had probably extreme nitrogen losses for some reasons. It's one risk. The second risk, it's a yield loss, because if this farmer apply extra nitrogen, we could see that it's an image also taken late season. You can see this dramatic nitrogen deficiency in this field. So we lose a lot of nitrogen because the majority of rainfall in Iowa comes from March through June. But that's not only nitrogen loss and yield loss, it's also reduced nitrogen availability because of moisture stress, which we also often have in August, late season. And this is the sidedress nitrogen application relative to anhydrous ammonia applied in spring. And what's the problem here, that we lose this nitrogen next year. So all of these are common risks in nitrogen management. Of course, you can ask that the yield loss here is huge. In fact, it's not. It's usually between 5–15%. So if average yield in Iowa is about 10–12 tons, the loss of yield for farmer 5% is very significant. So the question is, can we detect these yield losses? And one of the ways is to use in-season nitrogen diagnostic tools like speedometers. So this is the study I helped to complete and publish of one of my friends from Iowa State University. We had these 4 sites. We didn't apply any nitrogen in these corn sites. We then applied nitrogen early at V2, V3. This is liquid nitrogen applied at 5 nitrogen rate here on the bottom. So then we look at the temporal variability in these chlorophyll meter readings. And these are expressed as to the reference, as a relative readings to the reference to the highest rate. So what you can see here that we started seeing deficiency only after 2 weeks. So it took 2 weeks before we started seeing this deficiency. And then this deficiency progressed. And these are treatments that had yield differences larger than 10% from the reference. So it's clear that we could detect significant or large yield losses or yield deficiency in these fields, no doubt, by using the chlorophyll meter readings. But what if we apply extra nitrogen in season? We apply extra nitrogen, 56 kilo, 112 kilo, and these sites, and then we measured these relative chlorophyll meter readings again during the season, and what you can see that some of the treatments had recovered. So we corrected nitrogen deficiency, which is a good sign. But these are yield difference treatments with yield difference higher than 5%. So it's good news. We could correct and we could detect the differences because the critical chlorophyll, relative chlorophyll meter readings is about 95, 93%. But how about mild nitrogen deficiency? Here's all treatments that we could see yield difference less than 5%. And what it's clear here that all of these lines, all of these curves or lines merge, most of them merge. So what it says that it's very difficult to detect yield losses or mild nitrogen deficiency which produce less than 5% of yield loss. And that's relatively challenging. And why is that? Because some of these relative chlorophyll meter readings goes up. So there is a tendency to recover. They converge, almost converge with the reference rate. So it provides you some perspective how it's difficult in doing this in season and also create opportunity for other tools like sensor and other. But one of the reasons for this is because Iowa soils are high in organic matter, so soil will supply some nitrogen, about 50–60%, and these trends, these temporal trends, will converge. So the conclusion of this study is that, yes, we can use these tools and correct easily very severe nitrogen deficiency. But still, we need to focus on relatively mild deficiency and make them correct in appropriate time. The second conclusion that the canopy greenness of these plots had a tendency to recover. As we apply a small amount of nitrogen, they recover from these deficiencies, and that created additional challenge. And finally, what we found here that very often we see the increase in relative chlorophyll meter readings, but they don't produce significant yield response. So it's another challenge which allows us thinking more that other tools such as sensor may be more sensitive to detect this deficiency within fields. But it's not only this problem. We also face problem of making reliable nitrogen recommendation. And this is a poster. I was fortunate to work with late Dr. Alfred Blackmer from Iowa State University. He was professor of agronomy, and in his office, he had this poster laying on the ground, on his floor. And I knew this data were published, and this is collection of 54 yield response trials done in Iowa. They were published that had 7 nitrogen rates, and you can see these responses from a relatively high response to low response. And I asked him, what's the problem? And he told me, I don't know how to make recommendation. Which was kind of surprise to me. So I knew I still had like 2 years before finishing my degree, and I dived deeply in statistics and economics, and I was really surprised that he was true, he was correct. It's very difficult to make recommendation even using this big data set of yield response trials. One of the problems is that it's very difficult at the field level or trial level to identify which is the right model you can use to estimate this economical optimal nitrogen rates. This is just an example of a couple of trials. You may find this you know that we can use different models, exponential, quadratic, and other. For example, exponential is my favorite one, but it usually overestimates nitrogen rates. So recently we focused on quadratic and plateau, but you can see these are 68% confidence interval for these estimates, and yet they usually don't overlap. So it's an issue at the field level. But how about that across different trials? So one of the solutions we came up, which we eventually knew it was the right way, it's instead of using these response curves or these models, we focus on so-called discrete marginal analysis. What I mean by discrete marginal analysis, we look at the yields at each rate, and we look them as the yield response expressed as their per unit of nitrogen applied. It's so-called discrete marginal product economists use. So this is the difference. It's a yield response per kilo of nitrogen applied for each increment. And here's how it looks. So I have these yield responses per kilo of nitrogen applied across wide range of deficiencies. And you can see these products, these yield responses per kilo of nitrogen applied decreased. And what's interesting here that we can use the marginal cost of a kilo of nitrogen applied, in this case was about 5 kilo of grain, and we can estimate economical optimal rates without effect of these extreme high and extreme low nitrogen rates. So like in this case, corn of the corn would have these economic optimal rates, corn of the soybean would have this. In addition, we can move this line up and down and estimate other so-called benchmark optimal rates. For example, if farmer wants to get a profit about 20% for the last kilo, we can move this up and down and get additional benchmark nitrogen rates. So the solution to this problem was to try to classify this variability by categories. In this case, it's a previous crop, plus and avoid the effect of these extreme nitrogen rates by doing so-called discrete marginal analysis. And you may notice here that this relationship in this near-optimal range was near-nonlinear in this case. So again, the conclusion of this study was that we can avoid this problem by focusing more on aggregate data analysis or meta-analysis across different trials. And plus, we can focus on analysis of slopes, which those discrete marginal products, those are slopes. And finally, we can estimate different benchmarks for nitrogen rates, or optimal nitrogen rates. Plus, we can classify these, potentially, these trials by either previous crop, spatial variability, rainfall, and so on. So again, these are challenges when we combine all of these trials across different areas, time, and conditions. In economics, we usually focus on two estimates. It's after the fact and for the future, so-called ex post, ex ante. What I described you, we were focused on this. Of course, we had a problem of different with models and so on, but this is relatively small because in order to make reliable prediction and prescription, we have to deal with a lot of risk and uncertainty. And what I mean by this, it's a risk in spatial variability, it's a risk in prices, weather, differences in management. This is the big red box. In order to make reliable prediction or recommendation, we have to address these questions. And how? The question is how. So one of the solutions to this problem to quantify risk is to work with farmers and get data from farmers. So for the last couple of years, I've been employed by the Iowa Soybean Association, and I work for the group called Iowa On-Farm Network. It's a group which organizes farmers. We use different precision ag tools, which are shown here, and the objective is to teach farmers or to evaluate management using these tools. We usually work with about 400 farmers annually, and we also provide technical assistance to similar groups in Indiana and Minnesota. The core of these studies are focused on so-called adaptive management or participatory learning. The idea is to sit down with farmers and agronomists and develop plan what are the critical issues for them, then develop plan to collect critical data, analyze data, discuss this data, make interpretation, and finally, if it's needed, make adjustment for the future. This is the core philosophy idea for these studies. We employ different tools, and most of these tools to provide this feedback in nitrogen management. By feedback, I mean it's a final test, whether this practice works or not. So we employ different tools, and one of these tools is the late season digital aerial imagery shown here. We use imagery for different purposes. One purpose is to guide sampling of this field for the so-called delayed season stock nitrate test. We use the imagery to select sampling area for the stock nitrate test. We also use different replicated strip trials, which can be relatively complex and simple. So these are tools which provide the final nitrogen feedback or check for farmers. It's like the final test for students at university. So all of these results from this farmer's field are posted online. This is an example of this imagery with stock nitrate test. All of these results are online. You can go up and check. They have information about management, rainfall. And again, rainfall is very critical because without rainfall, it's very difficult to make any interpretation what this number mean. We also post all of the results for replicated strip trials. This is one example which has a treatment, yield, responses, some statistics, and some management. So again, all of these results are online. The key is we don't tell farmer's name and farmer location. We also developed so-called the database, online database of replicated strip trial results. And you can go online and check of this. So everyone, even you here in Canada, you can go and select year, crop, rotation. You can select different categories, different trials, and then you can check the results. This is the interface for this. It's a similar as a interface for the NAS. It's a National Agricultural Statistics Survey. So for example, if we focus on manure plus extra nitrogen, where this trial would tell where and when farmers should increase nitrogen rate for manure field, you can see the individual trials. You can see the statistic like average yield increased, the confidence interval. You can plug your prices for nitrogen, for corn. You can estimate return on investment. You can see what's the credibility interval for this return on investment on this extra nitrogen on this specific field. So all of this data are online. But one condition, we don't tell farmer's name and farmer's location. I want to show you some of the example which tells about the complexity and spatial variability we face in Iowa in terms of yield response in spade. This farmer, he wanted to know, he knew his no-till field, he knew this rate is about 140 kilogram per hectare on average, and he wanted to know whether he can reduce nitrogen rate spatially by 25 pounds per acre. So what he would do, he would apply field, this is 30 hectare fields, he would apply just 2 nitrogen rates in many strips across these big fields. And then we use yield monitor data, we estimate yield, and then we divide this field into cells and estimate yield difference, and we divide these differences into 2 classes, profitable and non-profitable. The black is profitable, the gray is non-profitable. So the question is, when and where farmer can increase nitrogen rate by 25 kilogram per nitrogen. So here's the data. He repeated these studies across several years, like this is the same field, 2004, 8, and 6, and 8. So we had the same field doing the same treatments over several years. And the question is, can we explain this variability in this categorical yield response? This is the same map, profitability map, only here it's a blue profitable, red is non-profitable. And then we employ a lot of different spatial factors like relative elevation, topographic wetness index, soil electric and conductivity, soil map, historical yield, a lot of different factors. So the question is, can we explain and predict this variability? So the farmer can reduce his nitrogen rate spatially by this small increment. You can notice how much variability we have in Iowa in terms of soil and elevation and so on. We employ so-called autologistic regression analysis. It's a spatial analysis of categories in space. So from these 15 fields, we found the significant effect of these spatial factors only in 8 fields. So we had 15 fields, and only in 8 fields we found significant effect. Like in this field, there was significant effect of relative elevation. So with increase in relative elevation, the probability of profitable yield increase went up because it's upward error. In this field, it was opposite. The higher elevation, the less probability, the lower probability of profitable yield response. So you can see that in different fields, we had different effect of different factors, and some of these factors did not agree. Only in this case, topographic wetness index had a similar trend. So the lower the field, the flatter the field, less likely to have yield response. Or the higher the field, the higher the elevation, the higher the slope, the more likely to have a significant yield response. So 8 fields of 15, we found these effects. So the bottom line is that, yes, we can detect this spatial effect, but unfortunately, these effects are not consistent over years, over time, which really brings a big challenge that there is something more than spatial variability, which I'll describe a little bit later. So just last Friday, we finished publishing a publication. It's called Adaptive Nitrogen Management. It was funded by Iowa INRS, and the key of this publication was to describe the system, how we can use this on farm studies and develop this decision support system. How can farmer use this information to make adjustments for the future? So all of these chapters here are focused on this development decision support system. This decision support system on this nitrogen feedback, or this, I would say it's a nitrogen checkup. So it's like a medical checkup. We recommend farmers to go this nitrogen checkup every year. So how they can use this nitrogen checkup and make adjustment for the future? It can be 3 levels. 1, if farmer use individual results and use rainfall data. The second, if we can use so-called benchmarking nitrogen rates across many trials, across many locations and years. And the last one, which is more complex, is focused on so-called multi-level analysis and estimated so-called predictive probability of risk. So in simple case, as I mentioned, Iowa is unique. About 60% of nitrogen losses occur in spring or June. So usually, as a proxy for nitrogen risk, we use rainfall. And this is spatial rainfall. These are interpolated 4-kilometer grids. These are data from radar. And as a proxy, we use about, if it's total cumulative rainfall from March through June is higher than 35 centimeters, we assume it's a relatively high risk of nitrogen loss. If it's less than 35 centimeters, we assume it's relatively low risk nitrogen loss. And here's if farmer use imagery and stock test for at least 2 years, here's this decision system, how a farmer can make adjustment for the future. If for 2 years, based on the imagery and stock test, the field, this field test optimal, we would say no significant adjustment, just watch out. If the field test excessive and it was the high above average rainfall, which means we lose some nitrogen, and still field test excessive, we would tell that farmer may not consider reducing nitrogen rates. So again, the logic, if the test showed that field is excessive based on the imagery and stock test, and still there were some losses, it means that farmer probably over-apply nitrogen. The exception if it's severe drought, limit nitrogen uptake. On the opposite side, if field is consistently deficient and there is an average or below average risk of nitrogen loss, it means that maybe farmer needs to think about increasing nitrogen availability. Maybe he will need to consider either increase rate or change the management practices, timing, forms, method, and so on. So this is a relatively simple logic how we can use this on-farm nitrogen checkup, I would tell, and make future adjustment for nitrogen management. Of course, this is for individual fields. It doesn't involve any differences in management. We know in Iowa we have different practices. So we classify these different practices into 5 major nitrogen management categories. So we combine the fall anhydrous ammonia as one practice, swine fall injected manure as a second, anhydrous ammonia spring as a third, liquid nitrogen apply in spring as the fourth, and citrus UN or anhydrous ammonia as a fifth. So we focus on timing and forms in terms of these 5 management categories. The last project we had, we combined all of the field we had for the last 7 years. So these are fields we sampled, we used the imagery and stock test, and some of them replicated strip trials, and looked what are the distribution of these nitrogen categories across these fields. Of course, different fields had different nitrogen rate and management. So we focus on so-called rates that produce the optimal corn nitrogen status for the field. These are distribution of nitrogen rates which farmers use, and they got optimal nitrogen status. This is for corn of the soybean, for corn of the corn, for these 5 different management categories: anhydrous ammonia, swine manure, and fall N. So what you can see, again, these are rates that produce the optimal field nitrogen status. So what you can see that there is a difference. These are kind of proxy for the economic optimal rates, because we know that where field is optimal based on the imagery and stock test, it doesn't have sense to apply extra nitrogen. So these are kind of proxy for economical optimal rates. So you can see that there is a difference between corn of the corn and corn of the soybean, and these are hundreds of fields. You may notice that there is a lot of variability for fall manure relative to this commercial nitrogen application. You would ask why we see the higher rates required to get optimal status for manure fields. First, we probably apply this manure too early. We lose more. Second, we don't know how much we apply with manure because it's so variable. Plus, maybe we increase demand for nitrogen because manure, it's not only nitrogen, it's something else. It's organic matter, it's PK, and so there are a lot of reasons. So this tells the red flag that we have to focus on these categories for these 2 rotation across Iowa. So if the farmer's rate falls outside of this box, it tells that he needs to think about why he is outside of this box, especially on the right side. Even if farmers use stock test imagery or replicated strip trial and he is still outside of the box, again, it's a nitrogen checkup. It tells why, maybe because of higher manure history or something else. So again, these are decision systems which can help farmers to focus on target area, like in this case. You can notice that less variability with spring application for these categories. And again, this is one of the levels of this nitrogen checkup or decision system. Of course, all of these have a different management too. The next step is to look at the relationship between corn nitrogen status, rainfall, and rates. Here's on the upper side of this image, we have a distribution of nitrogen status for these hundreds of fields in 2013. So this is corn of the soybean, corn of the corn. The yellow color, it's a percentage of deficient fields, marginal, optimal, and excessive. And what you can see from here, you can notice that corn of the corn had a tendency to have a higher nitrogen deficiency than corn of the corn. Liquid nitrogen applied in spring had the largest percentage of deficiency both in corn of the soybean and corn of the corn, especially corn of the soybean. And why is that? Look at the rainfall. This is the average rainfall for each of this category. In Iowa, the average normal rainfall for May would be about 10 centimeters. We had about 26, 28. So we probably lost a lot of nitrogen from the spring application because of 25% of this nitrogen is nitrate, right? And as soon as we get rain and we have a good drainage, artificial drainage, a lot of this nitrogen maybe goes up or goes down. You can notice that spring liquid nitrogen also had the highest percentage of nitrogen deficiency for corn of the corn. We can also look at which category had the lowest nitrogen rates, like anhydrous ammonia spring. We can also look which one of them had the lowest variability in rates that farmers use. And again, it tells the relatively differences between different management practices, including both rates, forms, timing, and placement as well. So what I described you were a kind of relatively simple decision support system. But of course, a lot of question is how we can incorporate directly yield response and economics. And in Iowa, last year, the state of Iowa had to develop so-called nutrient reduction strategy. Essentially, they're afraid that sometimes the government will impose regulation, and they want to be proactive and make assessment how we can reduce water or improve water quality through management. So one of the questions is, should farmers reduce nitrogen rates? So this is an example of more complex decision support system where the question was, what if farmer reduce nitrogen rates? What's the risk, and at which conditions they can reduce this, and at what risk? So this is a collection of trials we done a couple years ago. These are 2 treatment trials. A farmer would apply normal rate, and then he would apply the second rate, which was reduced by 30%. So here we both deal with spatial variability, and across different sites. We deal with these spatial yield responses. We call them yield loss. So we utilize a relatively complex analysis, but intuition is relatively simple. The question is, what's the risk of reducing nitrogen application at different factors? So we utilize so-called hierarchical analysis and Bayesian statistic. And what is useful about that, it allows us to make intelligent predictions for unobserved situations. Remember, in my course for these 54 trials, I only talk about ex-post. Here, I can make statement for the future in some sense. So the question is, I can use these different parameters, these different slopes at different levels, employing this analysis and estimate what's the risk of nitrogen reduction across different trials, categories, and weather and spatial variability. So here's what we found. And these are so-called nitrogen decision tree. It's one of the example. We have for two different scenarios. One, it's a dry May, dry June. The second is wet spring. So in dry conditions, for all fields, corn of the corn, corn of the soybean, the average predictive probabilities of economic yield loss was about 55%. Then we noticed that corn of the corn would, the economic yield losses predictive were less. So we would say that maybe we can reduce nitrogen application. Then we found that for citrus application in dry condition, the probability of economic yield loss was much higher than for spring application, because here with reduced nitrogen, with reduced moisture, a lot of this nitrogen is not taken up by plants. And moreover, it will be lost next year. So this is in relatively dry year. In relatively wet year, given these responses, what we found from farmers, we saw that probability of economical yield loss across all of the field was 80%. That's a lot. But still, we can narrow down and see that within field area with organic matter higher than 6% had a lower chance of economic yield loss. So again, this is the example using this multi-level analysis and this Bayesian statistic and these predictive probabilities, and we can classify this combination of these trials into different categories. So again, we have several levels of the decision system where a farmer use individual observation, use aggregate data, and we can use these on farm replicated strip trials to narrow down this probability. And again, the objective is to make adjustment or make intelligent predictions based on rainfall, management, rotation, and different spatial factors. So here's my final slide. Based on this, we kind of developed this system which allows farmer to go this annual nitrogen checkup. I know it's a nitrogen checkup. It's not pleasant. Some of the results are unexpected, even frustrated for different purposes, but we recommend them to go through, sit down, discuss, and then we develop specific tools that allows to use this information and help them make management decision. And the key is to quantify the risk. And I believe without farmers' input, without farmers' data, it would be very difficult to quantify this risk. And this risk is either nitrogen loss, it's a risk to be above or below optimal, it's a risk of yield loss, it's a risk of under or over applications. So this is the elements of this decision support system. The second key point, which I'm looking forward to discussing more, it's a multi-level analysis of this group of these trials. It's a very big issue as we accumulate more data, and hopefully we can come up with a relatively good ex-post estimate and hopefully a recommendation for the future. Because it's impossible to talk only about nitrogen rate. We have to incorporate the effect of management, timing, forms, and placement. And Tom will be talking about 4R concept. So this also nicely fit into 4R concept. Plus, we can incorporate spatial variability and rainfall. And finally, again, I'm kind of convinced that we have to, it's a two-way interaction between researchers, agronomists, and farmers. And this is sometimes very painful process because, again, it's a nitrogen checkup. You have to go, and there are a lot of unexplained and expected results. Sometimes we may be surprised, but that's a way the intuitive system works, and farmers will learn much better and quicker, and will trust us as scientists and researchers what we recommend them to do. So that's all what I have.
Thank you very much, Peter, for this very interesting presentation. We have time for some questions that could be in French or in English. So,
Léon Parent. I have a question about your multi-level system. Do you think that it would be a good idea to consider soil quality in this hierarchy?
The question was about multi-level analysis we employ with our replicated trial yield response. Well, it would be a good idea to put soil quality. Yes, we can put any factors, field level factors, or within field level factors. We can put in this system any observation we have. The question whether they are relevant for nitrogen management and explaining yield response, I would say that if these tests for soil quality really reflect some changes in management, I would assume the better the quality, the less nitrogen we need. That's my intuition. Hopefully. Of course, it can interact with rainfall. As I mentioned, in Iowa, the key factor is rainfall. It's when these losses occur and how we can prevent them.
There is the mic.
Thank you very much for your presentation. You did mention, while discussing your nitrogen decision tree test, that you were under dry condition, you were having higher loss with sidedress respect to spring and application. Can you comment on that?
Yeah, the question was in this specific situation, we saw that higher risk of economic yield loss with sidedress application rather than spring application. It's a dry condition. So what's happened in Iowa often, you sidedress and this nitrogen is not available because of lack of moisture. And of course, it's not direct threat in this year, but what happened next, we will lose this residual nitrogen in the fall and spring. So again, we have to know this risk. It doesn't happen every year. We know how often it happens. It usually happens in maybe once in 3 years. We have a data published in a journal of Saltwater Conservation Society, but it doesn't happen every year. But I think farmers need to know what is the risk. What are the odds if they use this practice, this specific practice or that practice? What are the odds to have this risk of being short or being seen this deficiency?
My name is Marie-Noëlle Tivierge. I'm a PhD student. I wonder if you use your discrete marginal analysis with manure, and if you did you consider the yield per kilogram of total nitrogen or per kilogram of ammonium?
Thank you for the question. The question was if we use the discrete marginal analysis concept for manure trials and whether we would use total N in manure or available N. In Iowa, mostly we use the total N. The studies show that, some of the studies show that about 90%, 190% of manure, nitrogen from manure is available, which is relatively, it's a ballpark. That's why we always track total N. Farmers supply us either manure analysis. Most of them, about 60% of this observation we collect, they have manure analysis. It may be not the exact load, exact farm, but they, because of manure management planning, they're required to collect manure samples. So all these rates, if I go back here, all of these manure rates are expressed as a total N. That's why we have so much variability. It's a red flag. It's an approach which tells us agronomists and farmers, here's the key area. We have to be focused on these because if we don't know how much nitrogen we apply, plus we don't know how much of this nitrogen is available in this specific season. So again, back to your question, these are total N, but the assumption is that a lot of this nitrogen is available, 100% is available, which is not true in most specific situation, because manure has some organic material. It may go through different type of decomposition patterns, mineralization, mobilization. So again, these are total N.
In Quebec, we have a different issue that in your state, we have excess water here. Like you're saying, after 14-inch, we have problems with humidity. Here, just only yesterday, we have about 6-inch in one day. So how you think your pattern can be transposed to Quebec situation?
The question was in terms of rainfall. Iowa has a different rainfall patterns. As I understand, Quebec has relatively uniform rainfall patterns across months. I would say that you have to focus to some extent. You have to know, because your rainfall patterns are much more predictable, I assume. No? No, you more or less. You can have a site-specific rainfall observation from either radar and maybe feed this specific rainfall observation in your management. But you have to establish how this rainfall affects nitrogen availability and nitrogen loss. You also have a large percentage of fields which have a artificial drainage, right? That's the same in Iowa. In central Iowa, we have a relatively poor drain fields, which also have a glacial origination. So a lot of these fields are drained. So somehow you have to connect rainfall and the risk of end loss by different mechanism. Either it's a runoff, mostly I assume it's a subsurface drainage. I agree, Iowa has different rainfall, but from my perspective, talking about nitrogen management without rainfall, it's very difficult because all of them interact in terms of loss and availability.
Alors, bonjour à tous, je suis Nora Ziyadi, chercheure scientifique à Agriculture Canada, ici à Québec. Donc, ma question, c'est, my question is related to the use of nitrogen use efficiency, slow release nitrogen in order to reduce the N losses or to increase nitrogen use efficiency. Did you try it?
The question was about using different products which will help to increase nitrogen use efficiency, specific slow-release nitrogen products like PCU, smart nitrogen, right, polycoated urea, or exactly. Slow-release nitrogen products. Yeah. Yes, we've done some studies in the past and been doing some currently. We don't have very solid conclusion either both ways. In some situations they work. And some don't. So I really don't have some of these studies should be online, actually, posted in our database.
What is the specific reason
why we don't see not nice performance?
Yeah.
Because again, it depends from timing and then rainfall. If we have below normal rainfall, lower losses, you wouldn't expect to see big benefits for this product in some situation. In some cases, farmers don't use, well, there is some trend maybe recently. I think even the state of Iowa recommend to use some of them as a part of the EQIP program in US, but we don't have a lot of data to go to recommend either way at this point.
Okay, thank you.
We still have place for one more question.
Bonjour, Gilles Bélanger, chercheur scientifique. I had a question on the what you call the optimal corn end status, and I understood that you measure that by measuring the nitrates in the corn stalks late in the season. Did I understand correctly?
Yes.
When you say late in the season, you mean?
It's after black layer, just before the harvest.
Okay, so have you thought of looking at using? You could use a chlorophyll meter readings. You could use whole plant tissue analyses. You could also use later at harvest, maybe the grain end concentration. Are those things that you've looked at to characterize the corn end status?
Yeah, the question is whether we look at the other different nitrogen diagnostic tools like tissue analysis, grain analysis. Historically, not in these projects, of course, taking grain samples from farmers are a little bit difficult. Someone needs to be there. And grain analysis has also, it only works very well in the deficient range. So a lot of diagnostic is focused on deficient range, very deficient range. In our case, we want to kind of capture both, using the imagery, capture the deficient range and stock test, which works better in optimal and above optimal ranges. So that's why we focus on these two tools, but some farmers use tissue analysis as well. Not often. It's some of the company are trying to develop a big database like DRIS database. It's been very common. Some of the company was accumulate more data. They are looking for kind of going back to the theory of DRIS. Maybe they can classify these trials and identify these critical categories for either grain samples or tissue samples.
So thank you very much again, Peter, for this
Thank you.
presentation.